Yes, ma'am.
So today we are going to see the non-bonded, right? Okay. So students, you guys have already until the bonded interactions, you have no doubts, right? We cleared, and today we are going to the non-bonded interactions, right? Okay. Now, you guys, no sound, no? Why you guys are keeping mum?
Yes, ma'am.
Okay, good. So today we are going to see the non-bonded interactions. What is that non-bonded interactions? What you guess if I say non-bonded interactions? Say something.
The electron pair isn't shared.
Okay. In biology, what could happen? Where you can, identify or observe this non-bonded interactions. Where you are able to understand this non-bonded interactions.
Hydrophobic interactions and van der Waals forces.
Then class I took one structure. Hmm? Okay, this was the structure. We last class I explained, right? See, every time when we see, for example, now let us consider the biomolecular system. Of course, it's like the example we take from a protein. Anybody is recording? Able to record? Okay, if anybody is able to record, you can record it. Okay. Okay. So students, like in the last class, we were like trying to understand the bonded system in one atomic system, two atomic system, three atomic system, and how to make a bond, how to represent the angle, so that if we were almost completely finished the connectivity which is observed in the atomic level connectivity which is observed in the protein molecules. The same is applicable for the nucleic acid, same is applicable with the carbohydrates, fatty acids, lipids, whatever you see. Okay. So the representation of a bonded network, when we see the problem from the designing perspective, then we have to represent each every atoms, we have to represent every diatomic system, we have to represent triatomic and all these things, it goes on. Okay. So there is also another one issue that we have to even consider the interactions between the non-bonded system. Suppose you have a protein, okay, this is a secondary structure. This is when you suppose you say this is alpha helix, and the alpha helix has a bonded system. So we know how to represent this bonded helix. But at the same time, that what is that electronegative groups, negative oxygen and the electropositive proton, they are sharing some kind of interaction between them that we already explained this as a hydrogen bond. Okay, so the biomolecule, what we have in our body, the main functional activity or functional form is modulated by the hydrogen bonds. Either the hydrogen bond is intramolecular. I use the word intra, intra. That means the same non-bonded interaction exists within the same molecule. But if I put this helix in a water medium, what happens? The same helix also form, in addition to this intra-hydrogen bonds, the same alpha helix forms hydrogen bonding interaction with a neighboring water molecule. So that is like inter-hydrogen bonds. or you can say that the hydrogen bond involved in the solvation of the helix. Okay, so there are so many things. So importance to the non-bonded interaction is very, very essential. That cannot be ignored, because that is the only or the main deriving force for any other biomolecular interacting. As I said, if you put in water, so this helix is interacting with the water molecule. Is it true?
Yes, ma'am.
Okay. As
Yes,
long
ma'am.
as, yeah, as long as the system is hydrophilic, the water molecules will get interacted. If the whatever your system, what you are modeling is hydrophobic, it will not get hydrogen, it will not share hydrogen bond with the surrounding water molecule. That is another additional information you should imagine. So when we say think about this hydrophobic, so the main point is the water molecules will not interact with the protein or the molecule what is your interest. Instead, the molecule will try to aggregate, try to concentrate its molecular mass in one particular confined region, probably a globular domain or some kind of, okay, when some kind of compact secondary structure, it will get it. So you can find the aggregation of molecule or like a closed geometry of a molecule when it is not interacting with the water. This water role and all we will study it later. I think in biophysics, introduction to biophysics, I have a exclusive topic on this water solvation. Okay, so apart from this water, suppose any cofactor is coming, any ligand is coming, how this will communicate? That has to sense. There should be a sensing mechanism between two different molecules. Either maybe one is a biomolecule, one is the new coming person. For example, every person when you are going to meet, you are not going to get introduced to all the people you meet it, but when there is a necessity or something you want to proceed, or you go and see some of your guide or some personal officer that you want to proceed for your next career, what you are going to do, you will go to his place and you will give your hand, shake hand and introduce yourself, and you start interacting between the person and you. There is an interaction, right? So similarly, if any foreign molecule that comes, that has to be sensed by the biomolecule what you are modeling. Or in the body, if you say some molecule complex is forming, okay, some protein A and protein B is interacting to form a complex structure. It has to come closer. It has to identify its possible interacting sites, and it has to create a non-bonding interaction between them. Then it goes in a very compact manner, similar, not very, almost similar to the bonded interactions. Okay, but this is little more apart. It is not that close like a bonded structure. That's what, even though these structures, I mean, these hydrogen bonds also make the complex, we consider them as a non-bonded interaction. It's not a bonded interaction. Okay. So such interaction should be given very, very essential important while modeling the structure. So what is this important is, okay, so I put non-bonded. Yeah, I think instead of drawing there's a picture I just saw. No, no. Okay, again I go to the screen. Okay, anything from 5 and 9. Okay, So today now we are going to see the non-bonded interaction. Okay, so for me, when I said there's a protein A, when I have another small protein that is also going to come and interact with this. Okay, so we are getting one complex. What is this complex? This protein A, then you have the incoming protein. Okay, let us say this PA and PB is forming a complex. You all agree with this? Say yes immediately, don't take time.
Yes,
Yeah,
ma'am.
okay.
Yes, ma'am.
So now our worry is like we have to characterize this region. Okay, so this region, we know to this represent this molecule as a bonded system. We know to represent this molecule as a bonded system, but here the interaction between PA and PB is a non-bonded interaction. Okay, so now we have to understand what are the types of non-bonded interactions. Okay, so the non-bonded interactions, we are worrying about Coulomb interactions. Then we are worrying about van der Waals. Okay, and we are worrying about hydrogen bond. These are the main things we are worrying about. Okay, so when a non-bonded interaction is there, you can classify this non-bonded interaction. One is Coulomb interaction, the other one is van der Waals, the other one is hydrogen bond. There are so many other things, like you can also find dipole-dipole interactions. What is dipole?
When a charge
Correct.
molecule.
Fine. Charge distribution. If the charges are not completely neutralized, if there is a separation between the distribution of two different polarities of the charges, then that creates a dipole. Understand? So what is a dipole? Everybody understand this dipole?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
So when you have a plus and minus and minus and plus, it is a, what is a neutralized system.
Neutral system.
But when you have the same charge plus and plus here and the minus and minus here, so there is a plus excess and the minus excess. So this behaves like a dipole. Okay, because of the charge redistribution. This is the important oh my god, redistribution. Please write it, okay, in your note. So now I'm coming back to this. So we have to classify, we have to now learn about the non-bonded interactions, but in the non-bonded interactions, based upon the distance between the interactions, you know, we are classifying the interaction Coulomb and van der Waals. Based upon the charged nature, we are going to talk about the hydrogen bonds. I think dipole I have not explicitly given, because it is like additional parameter we can consider in the force field. So now in the design of our force field, we have to consider bonded interaction plus non-bonded interactions. So the first component, bonded interaction, in the last class we saw, and today we are going to see the non-bonded interaction. Okay. Now I come to this one, Coulomb. What is this Coulomb? Everybody knows that a Coulomb interaction. What is a Coulomb interaction?
Ma'am, electrostatic interaction.
What is a Coulomb interaction? Suppose I have a charge Q1, yeah, electron R square. Then the Coulomb charge interaction is equal to Q1 multiplied by Q2 divided by r square. You all agree with this?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes. Okay. So important is this is charge driven interaction. So the sorry. So the charge of Q1, charge of Q2 should be sensed by the charge of Q1, but definitely there should be a distance between them. Okay, not too far, not too close. It is a moderate distance. Okay, so it is not too far. Okay, as well as not too close. Correct. So there is a charge interactions between the charge distribution. So you are going to have a Coulomb interaction. So this is equation number 1. The component number 1. Now we are talking about this van der Waals, which I explained in my previous classes, but I have not used the van der Waals term. You remember, let me put, this is the R and this is the energy. I'm going to repeat the whatever you already know only. Okay, so this is the E is equal to 0. Okay, so what happens? I have a atom A here. No, I am bringing another atom from the infinity. Suppose this is now infinity. Will there be any interaction between A and B? Is there any interaction between A and B when, okay, I located this A in one particular frame, but B is moving towards A to form an interaction. To begin the reaction, the B is in the infinite distance. Will there be any interaction between A and B?
No, ma'am.
No, ma'am.
Okay, so initial value will be 0. When the B tends to close this thing, slowly there's a 0 to some sensing, and what happens is like it will go like this. I will explain what is this. When you are bringing this B closer, for some regions it is trying to sense in attractive way. And one particular position, what happens? The atom A and the atom B both are closer, similar to the covalent in nature. Not closer to the covalent nature, but that will not form a covalent one. Okay, I tell you why. But let me finish this complete morphology of this graph. So the A and B will come closer. They will find out a stable interaction which is highly stabilized. How this is stabilized, I will explain it. Once you come again, if you come very closer, it is not acceptable because the nucleus charge repel, and the electrons and the electron repel. What happens? There's an agitation between the charges, so it goes to an unexpected high peak. So this region is not acceptable. This is a repulsive region which will happen, but the molecule will not form a closer interaction in this region. But here you see there's a sensing region, which suppose if I say this is a distance R1 from, it is not from infinity it will make, but some particular point it will make an interaction. That is what you have a reasonable, what is that, attractive region. But as a whole, I say the entire thing is an attractive region. Okay? You understand until now?
Yes, ma'am.
Yes, ma'am.
Oh,
Yes, ma'am.
okay. Okay, now I am going to explain this. Okay, so now we have a potential depth when compared to E is equal to 0. Okay, and what happens is when I say it's an atom, it's a nucleus, It's the electron cloud. And you have a nucleus and the electron cloud. When it is not bonding, what happens? This electron will repel. The nucleus will repel. But there's attraction between this nucleus to the electron cloud and this nucleus to the electron cloud. Okay, so this state is stabilized by the attractive interaction between the nucleus and the other electron cloud and this nucleus and this electron cloud. You understand? So there is a reasonable non-bonded interaction is existing due to the van der Waals nature. Why we are saying van der Waals? Because the scientist who worked on this, who established this concept, his name is van der Waals. Oh my God, my mouse. Okay. So we are now, this is different from this. Okay. What happens? This is a charge distribution everywhere. Okay. So you will have, what is that? Average distribution felt by other charges. So like Coulomb charge exists as long as you have a charge distribution. Okay, and this is this case, and this case is when you are bringing two molecules together, what will be the attractive part, what kind of repulsion will happen, and to some particular, it is sensing, it is making a stable interaction between them. So these kind of things we should endorse. This is little more longer than the Coulombs. Okay, this is short range interaction. This is long range interactions. You understand what I'm trying to say now?
Yes,
okay.
ma'am.
So when I talk about this energy of this, so we have to have a repulsive component plus we have to have an attractive component. Okay. So this attractive component is normally 1 divided by R power 12. And this repulsive is 1 divided by R power 6. So the energy when we represent will have a R power 6 factor, 1 divided by R power 6 factor, as well as 1 divided by R power 12 factor. So instead of telling this as a van der Waals, we can also say this is a 6-12 potential. If I say this as a 6-12 potential, you should immediately think that this is a van der Waals interaction. Okay? Yes?
Yes.
So,
Ma'am, I did not get that R to the power 6 and R to the power 12 part.
Okay. See, this part is the attractive part, and this is been identified that the contribution from this region to the interaction energy will be R power 12. Okay, and this part is the attractive part. This will contribute 1 divided by R power 6. So to write about the entire potential energy, I have to mention both attractive as well as the repulsion. That is 1 by R power 6 plus 1 by R power 12. Now you understood?
Yes, ma'am. Yes, ma'am.
Okay. So next I am coming to hydrogen bond. The hydrogen bond everybody knows. One atom, X atom, it has a proton. So it will have a delta plus. Now another, suppose I say Y, okay, this has a delta minus. So the delta plus, delta minus interaction is there. But who is the mediator? The proton. So two electronegative atoms, when they are like sharing their own closer vicinity due to the proton, then the hydrogen bond is mediated. So delta plus and delta minus, there's a charge distribution, and a charge distribution is stabilized by the hydrogen. So you have a hydrogen bond. I think in my previous class I explained, right? What is hydrogen bond? Some of them who are there in the biophysics class also must be already learned second time. So you know that the hydrogen bond. So two electronegative atoms, they can come closer and they make a strong, what is that, hydrogen bonding network. Okay, so this is like what is the order? Coulombs, then hydrogen bond, then van der Waals. So this is very closer. I think, yeah, I think hydrogen bond is very closer, then Coulomb, and then van der Waals. Okay, so these are the interactions that is taking care the entire non-bondular interactions. The one thing which I missed also, like a dipole-dipole interaction. So you have a dipole and you have a dipole. So it goes like that. What happens? This will interact, this will interact. So the charge distribution is stabilized by the dipole-dipole interaction. Let us not worry about this. Coming back to the slide, we are going to see the non-bonded interactions. What I explained, I think I remember. There is a mistake in the class itself. See, this is R power 6. This is R power 12 because this is a high energy. I forgot. I don't know why I forgot. Okay, so 1 minute. Okay, so now I'm coming to this issue that this van der Waals interactions act only at very short distances, but we are taking this region is a short distance. Okay, so attractive interactions are induced by dipoles between uncharged atoms. This is R power 6. Okay, then this repulsion is taken care of by this R power 12. So what happens when you are writing the potential or the energy? Okay, you have to have a two terms. One is 1 divided by Rij. Why Ij? Instead of AB, they have put Ij. So 12 power. This is the beginning stage because we are in the graph. We are coming. This we have this as the first term, and this the second term. So this one is the R power 6. Okay, so plus, now I am writing this Coulomb. So Q1, Q2 divided by 4 pi epsilon 0 R or R square. See, R square comes, normally when we have a complex explanation in physics, people take R square. But for a direct this thing, you can take a R square. Doesn't matter. So these two terms are forming the non-bonded interactions. So coming back to this, one more explanation. The long-range dispersion. We say van der Waals is also a dispersion forces. It can be described as classically as a simultaneously induced dipole-dipole interaction. Why it is a simultaneously induced dipole-dipole interaction? Because here the charge distribution or the charge repulsion is dependent on highly the position R. So according to the R, the charge distribution happens. That's what they mentioned this as a spontaneously induced dipole-dipole interaction. As R tends to infinity, the interaction scales up to R power 6. And the magnitude of force obviously depends on the strongly on the distance. So this distance matters. Whatever distance we are seeing, that matters. That talks about the strength of the van der Waals. Okay, and the short range repulsion is also there. So as I said, the dispersion that comes from the infinity to that one, it's a long range. Now we have a short range interaction, that is the repulsion. So this is a short range interaction, repulsion. So direct consequence of Pauli's exclusion principle. Why this upper increase in the energy is happening? The direct consequence of Pauli's exclusion principle. What is the Pauli's exclusion principle?
Electrons will be
No, two electrons in the same atom can have identical values for all the four quantum numbers.
Slowly, you tell. What is that? One person, tell me slowly.
Ma'am, the electrons would be filled from lower energies to higher energies in that order.
How this low energy comes? How this low energy comes? If this 1s2, sorry, this 2s2, will two upper electrons with upper spin is accommodatable?
No, ma'am.
No, ma'am.
Yeah. So anti-parallel. So one is upper spin with this one is lower spin. Then that only is a stabilized one. So this is the Pauli's exclusion principle. So suppose you have 2p3 means what will happen? The electron distribution.
Ma'am, one in each orbital.
Very good. So 1, 1, 1. After completing this only, this will start from reverse, one by one.
Yes,
Okay. Okay, that is what the sentence means. Okay, so this is the direct consequence of Pauli's exclusion principle. So what happens when this, okay, anyway, no problem. I'll go to slide here. Okay, so with this, what is that? Sorry, here. Okay, so this is frequently modeled as a 1 divided r power 12. And if we put together these two, this is taking care of the van der Waals interaction from infinity to the vicinity. Okay, so that is, you have a component r power 6. If I take this 1 minute. Hello. ஆமா சார், சொல்லுங்க சார், நான் மறந்துட்டேன் உங்களுக்கு. அது கும்பகோணம், தஞ்சாவூர் சேர்த்துருங்க. இல்ல நல்லா பண்றாங்க, நீங்க சேர்த்துருங்க சார். பயோடெக்னாலஜி ஒரு இது முடிச்சுட்டு ஒரு இன்னும் இப்ப வந்து பிஇ முடிச்சுட்டு எம்டெக் தானே போறாங்க. எம்இ எம்டெக்கா? நோ ப்ராப்ளம், நீங்க சேர்த்து விட்டுருங்க. நல்லா இருக்கு, ஒன்றும் ப்ராப்ளம் இல்லை. நெக்ஸ்ட் நீங்க பாண்டிச்சேரி யூனிவர்சிட்டிலே மூவ் பண்ணி விட்டுலாம். இங்க பயோடெக் நல்லா இருக்கு, பசங்க பிளேஸ்மெண்ட்டும் இருக்கு. சேர்த்துடலாம், ஒரு ப்ராப்ளம் இல்லை. அங்க பிடெக் இல்ல, இங்க ஆக்சுவலி இங்க எம்எஸ்சி தான் இருக்கு எனக்கு, எம்எஸ்சி பயோடெக். இப்ப அவங்க போறது பிஎஸ்சி பயோடெக்கா? ஆக்சுவலி பிடெக் ஜாயின் பண்ணி விட்டுருங்க. இவங்க கிட்ட எம்எஸ்சியா எம்டெக்கா நான் கன்ஃபார்ம் பண்ணிக்கிறேன். நோ ப்ராப்ளம். சாரி, ஏன்னா நீங்க கால் பண்ண டைம்ல அந்த அம்மா அவுட் ஆஃப் ஸ்டேஷன்ல ஒரு 2 வீக்ஸ் இருந்தாங்க. அதனால எனக்கு உடனே உங்களுக்கு பதில் சொல்ல முடியல. சாஸ்திரா நல்லா தான் பண்றாங்க பயோடெக், நீங்க ஜாயின் பண்ணி விடலாம். ஆமா, ஏன்னா +2 லெவல்ல வேற எங்கேயும் விடாதீங்க, அது கொஞ்சம் டிசிப்ளின்டா இருக்கும். நாங்க பாண்டிச்சேரி யூனிவர்சிட்டி கொஞ்சம் பயப்படுவோம். ஓகே. இல்ல பயோடெக் எல்லாம் இப்போ எமர்ஜிங் தான். நம்ம கொஞ்சம் நல்லா படிச்சா போதும், நமக்கு கம்பெனியும் போகலாம், ரிசர்ச்சும் போகலாம், எதுலயும் போகலாம். நான் கிளாஸ்ல இருக்கேன் சார், நான் அப்புறம் பேசுறேன் உங்களுக்கு. ஓகே சார். பை. Sorry guys. Okay, so this is so we have to combine these two things and we have to work on this potential. So when it is coming, what is the next? Okay, the same equation only. Wait. when it is coming for the calculation of the non-bonded thing, we will not worry about modeling the van der Waals interaction from infinity. We will take some effective regions. Okay, so we will cut these regions. Okay, and we will also cut these regions. Okay, so our focus to calculate, because this is a time consuming one. Okay, to focus this on, there should be some color. Okay. So we will focus on only these regions. Okay, we will not worry about anything because not this close. I think probably some 10 angstrom will fix, and then we will take like this. Okay, so instead of spending the time to calculate their interaction, this we will ignore these regions. Okay, so we will fix some kind of distance cutoff, and we use this in our calculation. This we will explain it later, not now. Okay, but you can keep this in mind, saying that even though the van der Waals, you have a very huge different nature of regions, this we will not consider, this we will not consider. Instead of considering this, we will find some kind of some function, some mathematical function, because when I cut this function, this is going to be a discontinuous function, correct? In a potential energy, if you are calculating only these regions, okay, and you ignore this, means the potential as it is will stay like this. How it will stay like this? So if you are drawing a graph, okay, and you are supposed to get your van der Waals like this, but what you are going to do is you are going to have your van der Waals region between somewhere like this. Okay, somewhere like this. What happens? You are ignoring this region. Okay, you are ignoring this region, and you are ignoring this interactions. So any discontinuity in the calculation of the energy is not what is that favorable, because every discontinuous function will emerge to give a error. Okay, so in the future I am going to explain something that we are going to use some mathematical approximation of this, saying that I make one representation of another polynomial and another polynomial, saying that okay, this system starts with the energy 0 and coming to energy minimum and having, suppose like this. So some energy to some extent positive. So mostly the positive we will ignore. Okay, this is kind of, these are the things I will explain it later, but as a van der Waals energy, we will limit with a particular R. Okay, so that, see, I am talking about now the van der Waals energy between A and B. This is 2 atoms, right? Suppose if I have a n atoms, I have to count n by 2 pairs. Correct. So AB is a 1 pair. Okay. So this the system has to go with n by 2 pairs. So we have n by 2 pairs in permutation combination. What is the? Suppose if I take with 1 2, then I have to take with 1 3. Now 1 2, if there is a non-bonded interaction additionally, they're normally 1 4 1 5. So normally we have 1 5. Okay, and this 1 2 1 3 1 4, everything we have to check. Then we have to 2 1 2 3 and 2 4. So everything is a permutation combination. This is considered as a statistical points. Each atoms we consider 2 to the power 1. So we make all permutation combination. All permutation combination. Okay. Now I am drawing like this. Okay. So I can do little more decent. This with the 2 and 3. 1, 2, and 3. 1, 2, and 3. So this permutation combination should be acceptable for this Lennard-Jones. When it is acceptable, by general you will take these pairs, but once it satisfies the van der Waals condition, then we have to calculate and we have to sum it. Okay, that is the entire van der Waals region that we are worrying about. So everywhere you see a summation, and the summation I and j should not be equal. We have to have this I is less than j. Okay, so if I is 1, j should be 2, 3, 4, 5, 6, 7, 8, 9, it goes like that. So this is the interaction normally we account. What is the interaction we missed? That is the hydrogen bond interaction. How this hydrogen bond interaction is taken care? Okay. So as I explained, we have a delta plus delta minus in between one hydrogen is there. It is going to, see this is an example with water molecule. Water molecule 1, 2 and 3. You guys are online?
Yes,
Yes,
ma'am.
Yes, ma'am.
Yes, ma'am.
yes, ma'am.
Okay. So there is a proton and again it is sensing the electronegative. This is oxygen. So this is O2 delta 2 minus. This is delta 1 plus. So 2 proton is required to satisfy delta 2 minus. So 1 oxygen senses 2 protons. Okay, so you also have a repulsion as well as an attraction. Here the attraction is little more R power 10. It is not R power 6. So instead of hydrogen bond, we can also say this as a 10, 12 potential. Okay, so that is 612 potential. This is 1012 potential. Okay, so you have the same. This is a hydrogen bond. So keeping this, instead of this bond, angle, dihedral, and the improper, I'm adding 2 exclusive terms. One is for the Coulomb, one is for the Coulomb, the another is for the, what is that? Lennard-Jones, plus you have a exclusive hydrogen bonds. Plus so many factors can go if your system is like highly dipolar in nature, or some, suppose if you are modeling, what is the dielectric distribution. Okay, so counterions should be there. So in that case, you will have more components of this energy. But this is the standard components that we bring the notice under this non-bonded, under this force field generation. You understand what is until now? So today we covered the non-bonded interactions, and now you know any force field for a molecule that should comprise the components from the bonded interaction, also from the non-bonded interaction. Is it clear until now? Students,
Yes, ma'am.
you guys are there? You
Yes,
are not
ma'am.
sleeping.
Yes, ma'am.
How many of you are
Yes, ma'am.
sleeping? Huh? You are
Ma'am, you said
sleeping?
speaking. Ma'am, you said speaking.
No, I was asking sleeping.
Oh, no.
So how many of you are sleeping? Uh-huh. So how many of you are speaking?
Ma'am, if they are sleeping, they won't respond.
Yeah, that's what. If there is no response, I can guess no. That's what I'm saying. Uh-huh. So you all have cleared what is non-bonded, what is bonded, right? No more confusion, right? It looks nice when you wave your hand. We guys are very much used to this virtual class now, right?
Yes, ma'am, but we don't like it so much. We like offline only.
Yes, yes. Even we miss. Our classrooms are empty. Okay, so everybody understood. So there is no problem with the MD so far, right?
No, ma'am.
No, ma'am.
Okay, ma'am.
No, ma'am.
Okay. So can I ask you one thing? Like next Monday onwards, shall we start the class 8:45 and I can break in between? 1 minute. ஸ்ரீ, நான் கிளாஸ்ல இருக்கேன், 1/2 hour கழிச்சு வரேன். ஏன், என்னாச்சு? நான் பாக்குறேன் நான். Okay, so I can break in between. Suppose you say 9:15 to 9:45, I can break. But shall we start 8:45 so that 8:45 to 9:15, half an hour, then 9:45 to 10:30. So I may have some extra half an hour or something. Is it okay?
Yes, ma'am.
You can think.
Okay,
you can pass on, because like we are going little slow, and this online also, like, it takes some time. So if I make use of, anyway, sometimes I'm coming 10 minutes late, no, so I can compensate that time also there, because morning somehow I am stuck from some 9:15 to 9:45. I'm little stuck. So I will not say that every day it happens, but most of the day it happens for me. So if we start 8:45, I can go with at least 9:15. Then I can leave you for breakfast. So 9:15 to 9:45, you can have your breakfast. Then 9:45 to 10:30, we can take it. In between 5 minutes, we speak also, we will have enough time to learn. Is that fine? No sound?
Yes, ma'am. Fine.
Okay, ma'am.
Fine.
Okay, ma'am.
Okay, ma'am.
Yeah. Okay then. So we will see you in the next class. And one request, this 519 Thursday, this Thursday morning also I am occupied. Any possibility to